Okay, let's continue our discussion of heaps, and I think perhaps what we'll do here is we'll declare a public class heap. Let me make my pen a little thinner. And our heap is basically going to look like the following. It's going to be an array. We're going to declare a static array. We'll call this the heap. We're going to have a variable over here. We'll call it current size. And actually, this variable will have a couple of uses for it. In our constructor, we would initialize this to 0. So that would indicate that there are currently 0 elements in here. But when I want to push new elements onto the heap, I'm going to use this as an index into here. So what a push would do is I'm going to push a value. I would push it to the 0th entry, and then I would increment this by 1. Likewise, we're going to be using this in a slightly different manner. When we pop, we will be decrementing this. So there's going to be a current size, and there'll also be a max size, just so that we can check on the size of this thing. So I'm going to come over here and I'm going to say private int, and that's an array, the heap. There is private int current size, and there is private int max size. And I'm not going to go through a whole lot of the details here, but we can imagine the following. We can imagine that there is a public heap that comes in with a single parameter, an integer, how big we want to make this thing. And we would just come over here and we would say something like the following: the heap equals new int size. We would come over here and we would say that current size equals 0. And we would come over here and say that max size is equal to SZ. And again, we would probably have another constructor with no parameter with a default size of, I don't know, 10 or 20 or 100 or something like that. You may recall from the previous tape, lecture, what have you, we talked about the push and pop operation. And we said, imagine that we have a heap here. Maybe it looks like this. Here's 25. And what we would like to do is we would like to push some new value on here. Suppose I want to push, that's a 90. Let's suppose I want to push a 95. So we said basically the idea of what we wanted to do here is we would sort of think about putting the 95 there. Okay, so if we're talking about push, okay, so remember this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to go at 10. So remember at this point, current size, okay, before I put this number here, there are 10 elements in the array, so current size would be 10. So if I were going to be doing a push here, if I were going to be pushing in val, the first thing that I would do is I would say something like the heap of current size is equal to val. Okay, that's basically inserting the thing over here. Then I think what I would do is I would come over here, and remember we talked about what we need to do is we need to trickle this up, which means we basically would swap the 95 with the 30, because 95 is greater than 30, so there's now a 95 here. I would swap the 95 with the 90, so the 95 would make it up here, and I would compare this one with that one there, and it would stop because this would be the correct place to do it, to insert it. So I would say that the heap of current size is equal to val. I would say bubble up or trickle up. I think your author uses either word here. So I would say trickle up. And this is really getting to be a mess here. So let me rewrite it over here. Let's say we would be doing a public void push int val. And so we said over here that we would do the heap of current size is equal to val. Okay, then I would do a trickle up and I'm going to pass this in as a parameter, and we'll see why in a moment. Okay, so that would put everything in its proper order. And then what I need to do is I have to remember to increment current size. Current size plus plus. And that would be public void push. Okay. Public void would be public int pop. I'm going to come over here and I'm going to say int return val is equal to the heap of 0. Remember, when I do a pop, I'm going to come over here and I'm going to pop off the 100. That goes away. And then what I would do is I would take the last value in the heap. So first of all, let's insert this 90 over here. So I would have a 100, okay, and then over here on the right side it would be the same. It would be 63, 17. But over here the 95 has come up here. This would be 95. Then what would happen is I would come down here. Here would be 90. Okay. Down here would be 25. Down here would be 30. This would be 40. This would be 10 and 20. So if I were going to pop here now, the 100 would pop off. I would move the 30 up to here. Okay, and then what I would have to do is trickle this down to the right spot. And when I trickle it down, the 95 would come up here. Okay, then the 90 would come up there. Okay. Okay. So what would happen after I did so this was a trickle up. Over here I'm doing a trickle down. And we could see that what happened is the 30 would come up here. I would replace it with the 95. So I would get 95 up here. The right side would stay the same. But now, with the 30 here, I swap it with the 95, so now the 30 is here. What I do remember when I trickle down is I pick the child that is larger, so what would happen now is the 30 would come down to here and the 90 would go up to there. Now with the 30 here and there's a child of 25, it just stays right there. So this would be 30, this would be 25. Over here I would get 40, and over here I'd get 10 and 20. Okay, so let's think about what's going on here. Over here and in pop, okay, so I get the return value. Okay, then I would say that the heap of 0 gets the heap of current size. I'm going to move this over a little bit because I need the room. It's going to be current size minus 1. Remember, if there are 10 elements in the array, they go from 0 to 9. Okay, so that's why I would have my current size minus 1. Okay, what I would do over here is I would now say trickle down 0, and then I would say current size minus minus. Okay? So now I just have 2 more things to do. I need to write trickle up, and I need to write trickle down. Okay, so why don't we work on push first? So I'm going to come over here, and we need a lot of real estate here. Please give me a moment. I'm going to need some more places to write on. So there we go. Okay, so let's draw a picture of what's going on, and then we'll figure out some code how to do this. So first of all, we're working on trickle up here. So let's just trickle up. So for example, here's a heap. Let's come over here and put some more numbers. Let's put a 1 there. Okay, so the idea here is we come over here. So first of all, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's going to come over here, whatever number goes in there, is going to have the value 10. Okay, so remember this would be 4. Okay, I go 4 minus 1 is 3 divided by 2. Here's 1. Here's 0. Okay, so the idea here is that I've just, okay, in my push, I have said the heap of current size would be 10. Okay, some new value. So let's suppose the new value is 95. Okay, and now what I need to do is I need to do a trickle up with this 10 here. Okay, so the idea, what I'm going to do is I'm going to come in here with a temporary value. I'm just going to call it temp. And what I'm going to do over here is I'm going to put the value in there. And the idea here is this is sort of like inserting into an ordered array. Well, where's the ordered array here? The ordered array is if I just follow the path up here to its parent. Okay, I've got a 50, a 90, and a 100. So this almost looks like code that we've seen before, but it's a little bit trickier because what we need to do is we need to keep track of the current place where we are and of the parent. So in other words, we don't know if we got to the parent by coming up this way or by coming up this way. So what I'm going to do is I'm going to come over here and I'm going to set current is equal to 10. And I'm going to come over here and I'm going to say that parent is equal to 4. Okay? And basically what I want to do is I want to say the following. And we're going to have to change this. This isn't going to quite work, but I think you're going to get the idea. I am going to say while, and I'm going to look at the parent, and I'm going to say while the heap of parent is less than temp, okay, so the heap of parent is less than temp. What do I want to do? Well, I want to copy this down to here. So I'm going to come in here and I'm going to say the heap of current is equal to the heap of parent. So what that does is that's copied the 50 down to here. So now this becomes 50. Let me just indicate that. So I've got 50 over here. And now what I want to do is I want current to be parent, and I want parent to equal its parent. So then what I'm going to do is I'm going to say current equals parent. And then I want parent to equal, now remember the way we find the parent. We go parent minus 1 divided by 2. And that's the end of my loop. And I apologize for this thing being so messy. Let's clean it up a little bit here. Okay, so I might come over here and I'm going to say something like the following. And we're still not done. We're going to have to figure out a few things here. So I say while the heap of parent well, that's less than temp. I just have this loop here, and it says the heap of current is equal to the heap of parent okay, and then I'm going to let current equal parent. And then I'm going to come over here and I'm going to let parent be equal to its parent. Okay. Now in this situation over here, remember I have temp as this, so at this point this is current and this is parent. And what's going to happen? Well, I still have that the heap of parent is less than temp. So I'm going to move things down. So now what's going to happen over here this is now going to become 90. And what's going to happen is this is going to become current. And this is going to become parent. Okay? And now what happens is the heap of parent is not less than temp. The heap of parent is greater than temp. So I'm going to jump out of the loop. And it's obvious that where I want to insert the new element is right over here at current. So I would come over here and I would say the heap of current is equal to temp. Okay, and we've inserted it in the correct place. Now, we're not quite there yet, but we're almost there. I have a couple of situations here. So in this case over here, let's just update the picture here. So if I'm inserting 95, the 95 is here. I now have this, looks like this, okay? And then remember what I do in the end now is now I increment current size. Current size would now go up to 11. That's fine, okay? But here is the question that I have. Okay, it's the endpoints. In other words, what happens if I insert, if the number is the biggest? For example, I wanted to push, in this situation over here, suppose I wanted to push 200. Okay, and the other thing I want to consider is suppose the number I want to push is actually right where it belongs. Okay, so in this case, let's suppose over here, suppose now this is what my heap is, and I'm going to push 1. Okay, well, first of all, let's consider the one over here of pushing 1. So if I push 1, I'm talking about, am I going to be able to add this one right over here? And I don't know if you can tell by the drawing, but that's supposed to go to the left. And if we were to do that, let's think about a couple of things here. It'd be 0, 1, 2, 3, 4. Here's 5. Here's 6. Here's 7, 8, 9, 10. So this would be 11. So what would happen here is his current would be 11. And parent would be 5. And we would come over here and we'd say, while the heap of parent, okay, well, the heap of parent would be the number 3. While that's less than temp, less than 1, well, it isn't. This is immediately false. And I would jump out here and it would say, okay, let the heap of current, which is 11, be temp. And it would insert that in the correct place. So this works fine. No problem there. Okay? Now, the question is, suppose I were pushing a 200. Suppose instead of this being a 1, let me get the eraser. Suppose now what I'm doing is I'm pushing a 200. Okay, so first of all, remember when I'm pushing a 200, so here, temp is 200, and current is equal to 11, and parent is equal to 5. Now what happens, so this is 0, 1, 2. So at some point, okay, this will be parent, and this will be current, and then we're going to go up even one more, and this will be parent, and this will be current. So let's think about what's going to happen. At some point, this is parent, and this is current. So at some point, parent goes all the way up to 0, and current goes up to 2. And let's go ahead and do it. And it says, while the heap of parent is less than temp, well, that is true. So then it's going to say, let the heap of current equal the heap of parent. So we would move the 100 down to here, and parent would be parent minus 1 div 2. Well, I've got a problem here. First of all, what is 0 minus 1 div 2? You know, I don't know. I have no idea what that is. Well, 0 minus 1 is a minus 1. Minus 1 div 2. Is that going to equal 0? Okay, but first of all, what's going to happen over here is this current is going to get to parent. So current is going to get to 0. So current's going to get to 0. And parent's going to equal, I don't know what. Well, I get around that problem really easy. what I'm going to do is I'm going to come up here and I am just going to rewrite this very simply. And I say, what I want my condition to be here is I want to say while current doesn't equal 0 and the heap of parent is less than temp. Okay, if I do that, because watch what happens. Once current equals 0, that means it's where it's got to get inserted, and we would come over in here and we would insert the 200. So that works. So basically, I have my public void trickle up, and I'm just going to say int where, and I'm going to come over here and I'm going to say temp is equal to the heap of where. I'm going to come over here, that should be int. I'm going to say int current is equal to where. I'm going to say int parent is equal to current minus 1 divided by 2. And now I just go into this loop. Well, current doesn't equal 0. And the heap of parent is less than temp. What do I want to do? Well, I shift things down. And then I update current and parent. Finally, what I do down here is I insert the element. The heap of current equals temp. And that's it. Okay, so we've taken care of the trickle up. We've taken care of pushing a new value on there. The last one is pop. I'm going to take the easy way out on this. I'm going to refer you to your book. But we have, let's see if we can find it. Was it way back here? Here's the heap. I don't think we need that one. We have push. So we've done trickle up. Where is slide number 3? Okay, here we go. So that was taking care of push. We have pop, okay, where we can see that, remember pop, actually there's a mistake over here. It's a good thing that we're here, because what we would need to do over here is return the ret val that we got off the top of the heap. Here you can see we've saved the top of the heap to return. We've taken the last value in the heap and assigned it to the top of the heap. And then what we have to do is we have to trickle it down to the right place. I can sort of sketch the idea here for you. What we have to do is, remember, we've inserted some new value here, and maybe this is a 30, and over here we have a 90, and over here we have 107, and over here there might be 40, 60, 32, 5, I don't know, 10, 3. So the idea of trickling this down, what we need to do is we need to look at both of the children over here, and we need to see which one of these is bigger. And clearly this is the bigger child. So if that's the bigger child, we need to do the swap between here and here. So that would result now in 107 being up at the top, and then over here there would be 90, and over here there would be 30. Okay, and this would continue to go down as it did before. Okay, but now with the 30 over here, there's a 32 over here, and there's a 5 there. And again, what I need to do, now that I'm looking at this one, I have to find the bigger of these two, and I have to swap it with that. So what that would do is that, of course, would leave me with a resulting tree that would look like this. A 107, here's 90. This continues to look like it did before, but now I would come over here and there would be a 32 over here, and then over here there would be 30 and 5. And this trickled down to the appropriate place that it needed to trickle down to. Okay, so I'm going to refer you to your book to actually look at the code for that. It's a little bit more complicated than what we've seen. It's on page 594. Okay, conceptually it's very simple. All right, I just want to bring up one more point here before we finish out this particular video. Let us draw a heap. And let's come over here. Okay, now you may recall when we wrote trickle up and trickle down, what we did is we actually gave a parameter. For trickle down, this was usually 0. For trickle up, this was usually the last element in the array. But we could actually stick any number in here that we want that's within the range of the heap. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In other words, here's the reason why we do that, because it turns out that these are a little bit more useful. Let us suppose that these nodes here actually contained more than just these numbers. Like maybe in a node there is there's a number, so we might have 60, and it might be Bill, and it might be 3.29, and there might be some other information in there. Okay, but the heap is kept in order by this number here. Okay, so suppose I wanted to change this number. In other words, suppose I wanted to come over here and I wanted to change this number, and suppose I wanted to change it to 51, or suppose I wanted to change it to 97. Okay, well, we can see that if we change it, then this particular node is going to move around where it appears here in the heap. And the big trick here is what I could do is I could say trickle up 4, because that's where this particular thing lives in the heap, or I could say trickle down 4. Well, the question is when do I want to do what? Well, if I change this number to something smaller, in other words, if this became a 51, then it's clear that what I would want to do is I would want to trickle down. Okay? And it's clear that if the number here gets bigger, like if this number over here becomes 97, then I want to trickle up. So I basically would say if the new value is greater than the old value, then I would trickle up for else trickle down for. Okay, assuming that this is the one that I wanted to change. Okay, and why this is all very good, why heaps are really interesting things, is first of all, I want you to think about what is the complexity What's the complexity of push? Well, remember what it is. To put a new value in here, if I'm going to put a new value in here, I stick it down here, and then what I do is I do this trickle up. Well, how bad can this be? The worst it's going to go is I have to go all the way to the top, up to here. And the complexity of that is just going to be log n. Okay? This is a completely balanced tree. If I have n elements in it, log n. The complexity of pop okay? If I do a pop, this guy goes away. I move this up to the top, and I do a trickle down. It's log n. So if you think about your binary search trees, your linked lists, and compare this always has a worse time complexity of inserting and removing of log n. That's actually a very, very desirable property to have. And in fact, we've talked about this before. If you wanted to implement a priority queue, okay, we've talked about doing this with ordered arrays. We've talked about doing this with linked lists. In other words, in both of these cases here, it could be the case that insertion could take up to order n if there are n elements in the array. Over here, it's always going to be log n. And over here, it's always going to be log n. So in fact, for a priority queue, a heap is a desirable data structure to use. Okay, the last thing that we're going to talk about here, we're going to get up to our next advanced sorting algorithm, and that is going to be a thing called heap sort. And we will take care of that in the next video. So bye-bye from Mission Control.